later. There's a couple sort of themes that pop up in these problems, and that is that first thing you have to do is you have to figure out what geometric object is being investigated. So in this homework 10, let me just get the specifics. What was it? You need to do a cylinder, and you're restricted to the fact that its volume has to be a specific size, right? So you said this, what number? I'm losing my mind. What is this? Number 3, 4? Number 4. So we have a cylinder. So let's get red out since my can is red. And so a cylinder is sketched, and this is a very poor sketch, but it's a sketch nonetheless. It looks something like this, right? So look, this is what we do. You might think this is silly, but this is exactly what we do in science. We simplify things. For example, if we wanted to study the blood moving through your arteries and veins, we know your veins aren't perfect cylinders. We know they're not like a garden hose, but that's what we assume they look like. We simplify the thing. This can is not a perfect cylinder. It has sort of this indentation. It's not perfect. But if, for the sake of investigating and understanding the bigger pictures, we simplify things. And so here I have a cylinder, and I need its volume to be 400 centimeters cubed. And I want to minimize, so this is what I need, and I want to minimize materials. So a good rule of thumb, when we say want to minimize material, that is code word for minimize surface area. So what that means is you have to think about how is a cylinder constructed. And so if I look at this thing, a cylinder looks like, well, this can. But if we want to think about the materials that make it, now we're going to assume for the sake of argument that we're not going to have a tab on it. We're just going to have a perfect circle top, perfect circle bottom. So we're making assumptions here. And so the area that you need to be thinking about is, I'll call it SA. And what is it? Well, for those of you who don't know yet, it is pi r squared for the top plus pi r squared for the bottom. And then what are the sides? Well, it's not always clear to us what the sides are, but if I take scissors, think about my cylinder right here. If I took a knife and I sliced it vertically like this, and then what I could do is I can lay out the metal. And when I lay it flat, it's going to look like a rectangle. So if I lay it flat, the sides look like this. Does that make sense? So another way to think about it is, how can I construct a rectangle? I take a sheet of paper or anything flat, a rectangle, and I bend it together to form a circle. Does that make sense? In fact, that's almost certainly how this can was made. There was a piece of aluminum that's flat, and they molded around some cylindrical object. Okay, now what are the dimensions of this? Well, the dimensions, you have to be careful. We know that in general, a cylinder has a specific height. The top and bottom have to have a specific radius. And so if we use that, our deductive reasoning tells us the distance from here to here is 2 pi r, because that's the circumference of a circle. And this must be height. Does anybody have a question about that or comment? Does anybody have a question about this? Because you can't do the problem unless you realize this. Now, of course, you could have Googled cylinder and you could have found this out, but this is why. And so the missing piece here for the materials is this thing. What's the area of this? It's 2 pi r times h. So if you want this to be annotated, we could say this is the top, this is the bottom, and this is the sides. And so what we could do is we can just write this up, combine our like terms, and let's just, for sake of simplicity, we'll write this as 2 pi radius squared plus 2 times pi times radius times height. So this is the function you need to study. Now, the problem is I just lied to you because I said this is a function. And while it is a function, it's a function of two variables. And we're in Calculus 1 and we haven't studied that yet. We have studied functions of one variable. So what we need to do is figure out how to eliminate a variable. And so how do we eliminate a variable? Well, we look at what we call our constraint. This is our constraint. We know we need our cylinder to hold a specific volume, which happens to be 400 cubed. So what we need to do is we have to use that information to figure out how to turn this into something we're familiar with. So as we pointed out last week, we have two options. So to see those options, let's look at it. What is the volume of a sphere? Or excuse me, a cylinder. So note, volume is the pi r squared times height. That is volume. This is true for a cylinder. So for those of you who are unaware of what we would call fundamental shapes, or the basic shapes, a cylinder, and for that matter, when we define volume in general, and you define that in Calculus 2, volume of a three-dimensional object is its cross-sectional area times its height. So we need since V has to be 400, we obtain 400 equals pi r squared h. So what we have to do is we have to figure out, do we want to solve this for h or do we want to solve it for r squared or r? So if I go back, I look at this creature, I have two options. I can replace r in terms of h, or I can replace h in terms of r. It's going to turn out I'd like to do, it doesn't matter how you do it. I'm going to use h. I'm going to get rid of h. So we can solve for h. And when I do that, I get h is 400 divided by pi r squared. So then sub this into our area formula. So our area becomes 2 pi r squared r, 2 pi r squared plus 2 pi r, and instead of h, I plug in 400 over pi r squared. And so now I can simplify this. I get a function that's useful. So here's the function you need to study. So the important function is SA of r, which is 2 pi r squared plus 800 over r, because the pi's cancel and one of the r's cancels. So you need to study that function. I don't want to make assumptions, but in the past, when we do a problem like this, this is the part that students usually can't get. And for those of you who actually will do the homework, usually you guys are good once you understand what the function is. Not that you all won't do it, but. Does anybody have a question? So that's how you do 4. Now don't forget, and I can't emphasize this enough. Yes, you need to know how to determine when this function has a minimum. You need to know that you take the derivative. You need to know that you determine critical numbers. But what's most important is that you explain why your extremum is the desired extremum. And that means you have to refer to one of the derivative tests. Are you going to use the first derivative test, or are you going to use the second derivative test? It's not enough to just say it's a minimum because it's a critical number. That's not enough. That's not the complete story. So I've pointed to that fact a few times, and I really hope that if you don't get what that means, that you ask questions. All right. Does anybody have a comment on this? So just to remind you, what do? You take the derivative, find which values of r make the derivative 0, and then test them to see which one is, if any, are minimums. Of course, there's going to be a minimum. You would imagine there is. In real life, we know there has to be an answer to this. Okay. And you also said 4. Is that we're sub 5? Oh, this is one of my favorite problems. People always love real world. You always say, when do they use this in the real world? And then as soon as we show you, you cry because it's hard. Right? That's everybody bitches their whole life. When is math used in the real world? When? And then we show you examples and you get mad. It's such a funny thing. By the way, it's a good time to remind you, you guys should always learn math and then learn computers and then go understand finance. And then you'll have work for hedge funds and be rich. Do you ever want to do that? Quantitative analyst. Mucho dinero. All right, so the next problem, number 5, I'll help set this up too, is it's a type of problem that arises when we study these things. So I could phrase this problem in lots of different ways, and it's structurally the same problem. So here's the way we're going to set it up. Basically, here's the issue. We want to get cable from land to an island. And as you would imagine, in the real world, it is probably one price to lay cable underground, and it's probably another price to lay cable underwater. This makes sense. Think about it. Now, we're going to assume that it costs more money to lay it underwater. I don't know if that's true in real life. I would imagine it's true because you probably have to take boats out and lay it. You can't just drop cable. By the way, have you ever been curious as to how you get internet and phone all over the world? Do you ever think and research about how much underground cable there is and underwater cable? Do you ever pay attention to that? Do you ever see underwater cables, how they get internet? I know you guys think that like the internet's magic. I know that. And you're like, oh, I can call Europe. And you feel like it's just some like magic little thing, like a little bird flies your messages to Europe so you can talk. Have you ever thought about how that works? You guys it's a very strange role. You guys are very non-inquisitive. It's a very strange thing to me. I'll have to show you pictures. Well, while I'm waiting for this to load up, because I don't want to keep switching screens. So I'm pulling the assignment up on another, on the computer in the room so I can see the damn thing. Not going back. But for some strange reason, it's loading slower than 1994 internet. These are things that are curious to me, not my shoes, but you should buy shoes too. It's good for your Seoul. You ever wonder how we get how do we get internet all over the world? How can we, these are the things that I would get you to look at. It's pretty cool how all this stuff works. Think about it, like Facebook and Google fronted pretty much all this money so that you can have fast internet all over the world. There's a map of all, this is all the underwater cable. The things I teach you, I'll tell you what. Then you can even ask questions. How do they, whoever they are, lay underwater cables? And then there's cool videos that show you how to do it. It's actually quite fascinating. I know there's a good little GIF of it, GIF. You have to find. But anyhow, it's pretty cool how they do this. Oh, here's not a GIF, but it shows you how they do it. Anyhow, this is O'Grady's education for you. But anyhow, we're going to do a very dumbed down version of this problem. So here's what we have. We have a seashore right here. We have a city, which I'm going to call Math City. We'll illustrate it like this, right? And then we have water. So let's color this in. Water. And just for fun, we'll let you know that this is land. And then we have over here, we have a cell tower. And then somewhere out here, we have an island. And we need to get cable from the cell tower to the island. That's what we need to do. And we want to do it as cheaply as possible. So need to lay cable from the cell tower to the island. Now, as you would imagine, there's lots and lots of ways to do this. Perhaps I just lay it straight from the cell tower to the island. Perhaps I go all the way down land until I get to Math City, then I go straight up to the island. But you'll notice in the problem that due to the constraints of the problem, there is a point that we need to go down. So we're going to go down so far, land, and then we are going to shoot up to the island. If you read the sentence of the problem, I said determine the point where the underwater cable should meet the shore in order to minimize cost. So without us talking about this problem, it might be difficult for you to set it up if you haven't seen it before. But once we sort of tell you the situation, what we need to do is we need to take this scenario and we need to draw it in simplified terms. We need to think about it in a math world. And so what I'm going to do is I'm going to sketch a model of this. So here's my model. My model is I need to go from here up to here. And I don't know when I'm supposed to do that. So what I'm going to do is I'm going to use what I'm given in the problem. I am told, for example, that this distance is 10. I am told that this distance is 12. And so what I'm trying to figure out is, look, this schematic that I've drawn has covered every scenario that makes sense. This scenario, and by the way, this scenario right here, this scenario, I didn't say anything about how far this was. So if by the way, this is a right triangle. what I can do is I can introduce a variable. I can call this distance x. And then that means this distance is 12 minus x. Now, you might say, well, how would I have known to draw that? Well, maybe you wouldn't have, but now you know. We're simplifying the problem. Now notice, if x happens to be 0, that is the scenario. If x is 0, that is the scenario where I take my cable all the way down to Math City and straight up. If x is 12, that's the scenario where I go underwater the whole way. Now, any other scenario would be redundant if we're in this simplified model, because you know it's not going to be a curved path, because that would be longer, right? At least I'm telling you that. So under the constraints of the problem, there are 3 scenarios. So the first one is x equals 0, and this corresponds to taking cable from the tower to Math City, then north to the island. So let's look at a schematic of that. The schematic of that would be all the way over and then up. And we know this is 10, we know this is 12. And so the cost here, what is the cost? Well, given the problem, the cost here is 12 times 1,500 plus 10 times 2,500. Which, if you do the math, would be, in this scenario, $43,000. Okay, what is the second scenario? By the way, does anybody have a question? Well, the second scenario, let's look at that. Let's look at the second scenario where x equals 12. Well, this corresponds to running cable from tower to the island straight underwater. So if we draw that schematic, here's our right triangle. That's pretty bad. And I'm going to use the dotted line to suggest that there's not cable there. So this is 10, this is 12, and so this line, by the Pythagorean theorem, is 10 squared plus 12 squared. So here the cost, since it's all underwater, will be, what did I say the cost? I already forget. Was it 2,500? 2,500. So this would be, how many miles is it? It's the square root of 100 plus 144 times the cost, which is 25. So if we do the math there, this is equal to 39,051 and change. So it's approximately $39,051.25. So clearly this is cheaper than going all the way down and then up. Now the question is this the cheapest? Well, we've only calculated the cost of two scenarios. We haven't calculated the cost that what if I go down, land a little bit, and then up. Does anybody have a question about this? All right, so the interesting scenario is next. The third scenario, where x equals blah, this corresponds to some water after land, some lands and some water. So if I draw that picture, that's down to here, and then up. So if this is 10, we know this is x, and we know this guy is 12 minus x. What is this distance? Well, by the Pythagorean theorem, this distance is 100 plus x squared. Now here the cost depends on x, so now we have to do some analysis. It's not just arithmetic. Here the cost is a function of x. So cost is, well, let's do the land part. The land part is 12 minus x times 1,500 plus the water part, which is the square root of 100 plus x squared times 25. And so this is the function you need to analyze. So question you need to ask, does this have a minimum? And where does x range? We know where it ranges. It ranges between 0 and 12. And then not only does it have a minimum, is it cheaper than the 39,000? So this is not an easy problem by any means. But there's lots of problems of this ilk, and I'll show one with you in a second. That was famous a few years ago. Questions, comments about this particular problem? Yeah. Say that again.
So in bottom where it says have remaining for actually 3 0.
Yeah.
Wouldn't it doesn't really matter. Well, if it was 0 when it would be each of them be first and second.
Well, right. So it's not going to be 0 because we saw 0 is the most expensive of the first two scenarios. So the oh yeah. So but okay. So well, no, actually theoretically you couldn't. So I think your question is, the question was, can you just write this? Is this what you're suggesting? Just putting less than here? So no, theoretically this is not correct, because if you remember, we had this theorem called the extreme value theorem. And the extreme value theorem says that you can only guarantee a global min and a global max if you include your endpoints. So you have to, so the way this works, theoretically, you have to look at this function. You have to find the critical numbers, and there's going to be some. And then you have to determine, is that critical number a minimum? And if it is a minimum, is it smaller than the one endpoint, which is 39? It could be, it could not be. Yeah. Yeah. Correct. So look, here's what happens, and this is why I tell you to be careful with your words. A lot of students, particularly good students who do lots of practice, they'll start to realize that in a lot of these problems, there's only one critical number, so it has to be the correct answer. Well, the problem is, maybe, but if we move away from textbook problems that always have a simple solution, and we ask you to think a little more out there, like in the real world, then it's not always clear, right? So I mean, like I said, it is possible that this minimum, the way I decided to choose the prices, it's possible that there is a minimum here, but it's not the global minimum. It's possible that the cheapest route is straight from the cell tower to the end. Do you understand what I mean? And then in your scenario, you'd be wrong because you wouldn't be including the endpoints, right? Does that make sense? So yeah, you have to be careful. And look, we're not trying to trick you. I mean, the point of this problem is this is a hard problem. Clearly, most people do not even attempt this problem. You just skip it because you don't even know how to set it, right? But I would encourage you to try to understand it. And to build upon that, there's a sort of famous problem of the same thing. So let's look at the England. What was it? England. So a few years ago, there was this problem on this test that like high school students have to take in England, and everybody was all up in arms and mad. And so here's the problem, and it's almost identical. It's just it's themed differently. So it's worth showing. You're going to give us an ad. So essentially, the problem is, well, there's no sense in us watching it. You can watch it if you want. But the theme is the same. So the idea is that an alligator is going after a zebra, right? And it has to cross a body of water. And so we know an alligator is going to go one speed on land, and we know it's going to go different speed on water. So the idea is when should the alligator cross? And so the idea is the same, only in our problem, we're talking about cost. And so the cost would be the price per mile times how many miles. Whereas here, it's going to be your speed or your average speed. It's going to be, your speed on land times how many, your distance on land, and then your speed in water times how far you have to travel in water. So these are very sort of, these are, again, this theme of problem shows up oftentimes. So we could talk a similar problem with almost the same exact setup would be something like this, or me saying, you need to get from one side of the river to the other, but you don't want to go straight across. You want to go down that way. What's the quickest way to get there? And by the way, these are not just toy problems to screw you up. It's interesting. Animals often do calculus. It's funny. There was an article written not that long ago about like showing how dogs do calculus, like how do animals take certain angles.
And even if you think about it in sports, if you analyze how athletes, particularly like say a football player, you have a ball carrier running one direction with the ball. I mean, what we often do is in our head, we calculate what our speed is, what their speed is, and what angles. I mean, animals do that all the time to eat, which gets me on a point. Do you ever think about how wild it is that as humans, we're like one of the only species, if you believe we're animals, I don't know what some of you believe, that we don't have to wake up every day thinking we got to be faster than the person who wants to eat us, right? Right? And then we don't have to be fast in order to eat. We just go to the grocery store. Puts it in perspective. That poor zebra don't know what the hell is happening. He dead. You ever watch video? I like watching videos of like animals hunting other animals. It's wow. Nature. But anyhow, this is a good problem. All the Scottish kids were mad they couldn't figure it out. Okay, and by the way, this is also, I alluded to this, the problem we set up for you guys. Remember, I think it was 2 classes ago, and I said this is a hard problem. Maybe we should set it up different. The one with the cable from one height to the next and then meets at the bottom. I think we did that on Friday. We ended class with. We never finished it. I said perhaps we're setting it up wrong. This is also, these ideas are similar to how like we study light, and I told you that, how light travels. Have you ever, I said a good way to think about it is if you're standing outside of a body of water and someone's in the water and you look, and if their head's above water and then you look down, it looks like their body's shifting. Why is that? It has to do with how light goes through different mediums. And that's related to this too. So anyhow, this is fun stuff. Of course, you're going to say it's hard, and that's anything worth learning that's fun is difficult. Why not do it? All right. Any other questions on this homework? I think from my perspective, those are the 2 difficult ones. Problem 7's a little tricky. Problem 6, we already did that for you. And we basically did 8 and 9 last class anyhow. So hopefully you'll look at the notes and figure it out. 2 is not hard once you learn how to set it up, but most people don't set it up correctly. You guys don't like to read. Can you do 7? I don't know. Can we do it? Yeah, I'll set it up for you. Yeah. I'm not going to do it though. What's the fun in that? What's the fun in me doing it? Why? Oh yeah, don't you hate when teachers do that? I don't know, can you? It's may I, right? Shut up. Ain't, that's what I hate. Don't say that. You can't speak like that. I remember that when I was in high school. Don't speak like a Pittsburgher. You'll never get a job. Well, here I am. Don't say ain't. Here I am. Ain't. Of course, you have to know when you can speak like an idiot and when you shouldn't, right? You got to know when to play the game. That's important. You got to know when to wear a shirt and tie. You got to know when to look someone in the eye and be polite. You also need to know when to have fun. These things aren't always mutually exclusive. All right, so problem 7 says we have a parabola. And we'll remind you what this looks like. This guy, I don't need a graph per se to do it. I know that it's flipped upside down. I know that it goes through the point 0, 1, and it looks like this. Oh boy, hey, when that happens. So here's what the graph of my function. Oh my God, boy, vey. I'm gonna end up messing this. There we go, we fixed it. So it looks, here's a sketch of this thing. Now, I could actually determine these points. When does this equal 0? So the function we have is y equals 1 minus 1/2 x squared. So this thing equals 0. So this is what? 1 minus 1/2 x squared. So if you solve this for x, take 1 to the other side. This is the same as 2 equals x squared, right? And of course, that's the same thing as x equals plus or minus the root 2. So this point, for example, is root 2 comma 0. This point is negative root 2 comma 0. And so what we want to know is if we look at the point 1, 4, which is up here somewhere. Actually, it's, I'm being consistent, it's over here somewhere. And we want to know what point on here is closest to it. So this is very similar to the problem we did last week. The only difference is, or maybe we did it last week. The only difference is the function we get is going to be a little trickier. So you have to use your distance function. So you know that the distance between 1, 4 and any point is this. So it's x minus 1 quantity squared plus y minus 4 quantity squared. And then we're interested in what happens when you're on this curve. So here's what makes this brutally challenging, is I'm going to replace y with 1 minus 1/2 x squared. That's one way of doing this. And so now you have a function in terms of x, which is quite ugly. What I'm going to do, well, okay, let's go a little slower, not to scare you. So this is minus 3 minus 1/2 x squared quantity squared. Now, here's a little thing that can help ease the pain of this problem. You have two options. You can multiply everything out inside if you wanted. You don't have to. So this is the function you have to study. So the question is, does this have a min? And it's ugly. It's ugly calculus. It's ugly algebra. I can tell you that it does have a min. I mean, look at the picture, but can you find it? It's not an easy problem. So you have two options. Option one is to just leave it as is and carefully take a derivative. Option two is maybe multiply everything out inside first, then take the derivative. It doesn't matter how you do it. By the way, you can get rid of these negative signs if you wanted. And it's not that you just get rid of them because you don't like them. It's just you're squaring, right? So you could essentially factor a -1 out from each piece. And -1 squared is +1. So you could actually do this. And that'll make your life a little easier. You don't have to, but you can. Not a fun problem. But if you look at the problem, it's clear there's a solution. It's just that you got to figure out what it is. There's another little secret. I didn't mention this, but it could help you with problem 6 and problem 7. So let me give you a little hint that might help. Hint. And you should think about why this is true. If I write d is equal to this. So what was it? It was x minus 1 squared. I already forgot what it was. What? 3 plus 1/2 x squared. This, as you guys know, if I square both sides, is the same thing as this. And here's a cool fact. You should think about why. Cool fact. Solutions to d prime equals 0. So the critical numbers of this are the same as solutions to d squared prime equals 0. So really, you only need to study, and this is a good shortcut that will save you time. So this means you only need to analyze star. That'll save you some ugly derivatives. And you could think about why. It's the same thing I told you last class. Remember last time, not last class, but on Friday. Remember we did the one and I said, don't worry about what's in the radical downstairs because it doesn't matter. Because you're just going to clear the fractions anyhow. I don't know if that makes sense, but even if you don't understand why, you can simplify your life by doing this. Does anybody have any questions? By the way, it should be noted, you know what? Let's just finish this. Why not? It'll be fun. It should be noted when you take the derivative here, you're going to get a 4th degree polynomial. All right, so let's actually play the game. Let's do it. So 3 plus 1. Let's do it. Why not? So if you use the chain rule, it's 2 times x minus 1 times 1. And then when you use the chain rule on the next piece, you get 2. And then it's 3 plus 1/2 x squared times, you're just going to be left with x. So again, when I'm doing this derivative, I'm going to use the chain rule in both pieces. Bring down the 2, recopy. Derivative of the inside is 1. Here, bring down the 2, recopy 3 plus 1/2 x squared. And then the derivative of the inside is 2x over 2, which is just x. So this is the derivative. And this cleans up quite quickly. This is 2x minus 2. And then you're left with plus 6x. 2 and 3 is 6, and then you have an x. Plus the 2's cancel, x cubed. And so at the end of the day, this creature is x cubed plus 8x minus 2. And so at this point, you're feeling real good about yourself because you're like, okay, I've got done this. But we need to find out when this is equal to 0. And it turns out that ain't exactly easy to do. So before I go any further, does anybody have a question about what I did there? Going once? Yeah.
So when you say that the solution is d prime equals 0, it's saying that d squared prime equals 0. What do you mean exactly?
Okay, so here, so the question was why am I allowed to use d prime of d squared, is what you're saying. Okay, so just ignore for a second. Let's just think of a general scenario. So let's look at d squared. Now, just to be clear, this is a function of x, right? So let's look at d squared prime, and it equals stuff. I don't care what it is. In this particular problem, it equaled this stuff, right? Now, if I look at the left-hand side, if I rewrite that, d squared prime, by the chain rule, that is, what is it? Well, it becomes 2d times d prime, correct? And then this is equal to stuff, same stuff. Now, if d prime is equal to 0, so okay, let me think of it another way. if here's, let's solve this for d prime. So if I solve this for d prime, I get stuff over 2d, right? Now look at this. If stuff is equal to 0, then d prime is equal to 0, right? And if this stuff is equal to 0 here, then so either way, so if this is equal to 0, then this is 0. And if this is equal to 0, then this is 0. So the only thing that matters, the key is, and this is why I said last Friday that if you remember, when we did the problem, originally I put 2 square root of blah, and I said it doesn't matter, because when we go to solve it, it doesn't matter. Because when you set the left-hand side equal to 0, you're clearing it. You're multiplying both sides by it, and so it goes away. So the only thing that matters in that fraction is the numerator. And so it doesn't matter if I write it compactly like this, or if I write it out like this. So just make sure, it makes the amount of work required of you less. Does that make any sense? Yeah. So that's the way you think about it. All right, now, if that wasn't crazy enough, what stinks even more on ice is this creature. We have some bad news. X cubed plus 8x minus 2 equals 0 ain't easy to solve. And I'll put easy in parentheses. What I mean by that is all the techniques you learned in algebra class about factoring and all that, it ain't gonna work with this. It's a cubic and it doesn't factor simply. So how do you solve it? So here's another point that makes this problem difficult. So now you have options. Maybe you go to a computer and ask what the solution is. Calculate. So another way of thinking about this is that ponder your algebra knowledge, at least what we hope you have. You first learn how to solve linear equations. That's when there's no powers, like 2x plus 5 equals 13, something. And then you graduate to quadratic equations, and then you learn a few ways to solve them. You learn how to solve those first by like completing the squares. You might remember that. It's hellish nonsense. But then what you really do is you learn this shortcut called the quadratic formula. And then once you do second and first degree polynomials in an algebra class, then they say, well, what happens if the power's 3 or 4 or 5? And then really what you do is you only learn how to solve the ones that can be factored. This one cannot be factored, so it's hard to reason what the solution is. Now it turns out there's actually a formula for cubics, just like the quadratic formula, but it's impossible to memorize. It's ugly and no one would want you to know. And so the thing is, what do? So one option is we can go to Desmos. It's already up. From last class. If I go to Desmos and I graph y equals x cubed plus, what was it, 8x minus 2. And I'll notice that if I zoom out, it definitely crosses the x-axis. And by the way, we know it only crosses once. And Desmos tells us that it crosses around 0.248. So one option we can do for for this particular problem is we can use a computer to solve it or approximate the solution. So how would we properly write this? So we could say, using Desmos, the critical number is x approximately 0.2481. Now, this is not ideal, but it's the best we can do right now. Now, there are other ways to see this other than to just go to Desmos. So, but this is not the class to learn about those methods. By the way, a question that people bring up is you'll say, well, can I use Desmos to solve equations? Well, you can, but if you can determine an exact solution, we want exact solutions. Here we can't. So we do the next best thing, we approximate. I mean, this is a good approximation. It's not a bad approximation. You can keep zooming in on this. You're not going to get much better than 2480 or 8. Let's see, can we even get it to get to 80? Keep zooming in, would it? Oh, now I can get it. See, now I got a little better. So I know I'm accurate to at least 3 decimal places. Anyhow, let's look at the problem. We can go back and see that it does seem to be reasonable. What was our original? Our parabola was this, and we wanted to know which point was close to. Call this F. 1, 4. And so if I plot the point, what was it? So if I plot 0.2, 4, 8, 0, 9, comma F evaluated at 0.2, 4, 8, 0, 9, you'll see that that point indeed looks like the winner. Does anybody have a question about this? So it's not an easy problem, but now you know. But it is worth out. I do want to make a point about this because I don't want you guys to get it twisted. We only used Desmos to get an approximate solution because we couldn't get an exact solution. So let me make this very clear because I don't want you guys skipping out on all the fun math. Remark. We only approximated because we could not get the exact solution. So, and I've said this since the beginning of this class, and I'll say it over and over again. If you can get exact answers, that's what we want. So let me remind you, if exact answers can be obtained, you must obtain them. Now, of course, the question you're going to say is, well, how do I know? Well, if it's a first or second degree of polynomial, you can get exact answers. If it's higher degree and it can be factored, you can get exact answers. On an exam, I will never, ever lead you astray. If you can get an exact answer, I won't say anything. If it's a problem where you need to approximate, I will make sure you understand. Is that clear? I'm never going to leave you hung out to dry. So you should always assume exact answers are available unless otherwise stated. All right. Does anybody have a question? All right. Looks, time's up. I will see you tomorrow. Tomorrow is our what? Our second to last Friday class, right? Then we have 3 classes. Oh my God, the end is near. The end is near. All right, gang. Thank you very much. Have a good one. I will see you tomorrow, hopefully, and stay safe and curious to learn. That's my advice for today. All right, everybody. Thank you. Bye now.